Welcome to Cambridge IGCSE Physics, Lesson 41.1, Current in Series Circuits. Today we explore how electric current behaves in series circuits, a fundamental concept in electrical physics. This lesson covers core content essential for your Cambridge IGCSE Physics examination. We'll discover that current remains constant throughout a series circuit, understand why there are no branches in series connections, and learn proper measurement techniques. This knowledge forms the foundation for understanding electrical circuits in technology, from simple torch circuits to complex electronic devices. Let's begin our systematic exploration of current behavior in series circuits. Let's examine our learning objectives for today. By the end of this lesson, you'll be able to, first, know current is same at every point in series circuit. This means understanding that electric current does not change as it flows through components connected in series. Second, understand no branches in series. This refers to the single pathway characteristic of series circuits. Third, measure current in series circuits using proper techniques and apparatus. These objectives align with Cambridge IGCSE assessment focus. AO1 requires scientific knowledge and vocabulary, AO2 involves problem solving and pattern recognition, and AO3 covers experimental skills and investigations. Now let's define our key vocabulary. Each term is essential for understanding this lesson. First, series circuit, which means components connected in a single pathway with no branches. Electric current flows through each component in sequence. Second, current, which means the flow of electric charge through a conductor, measured in amperes using the symbol A. 1 ampere equals 1 coulomb of charge flowing per second. Third, ammeter, which means an instrument specifically designed to measure electric current connected in series with the circuit. Understanding these terms precisely is crucial. Remember to use SI units, the International System of Units, and proper scientific notation throughout your work. Let's explore our first core concept, series circuit fundamentals. The fundamental principle states that a series circuit provides a single pathway for current flow. This means electric current has only one route through the circuit. The definition is, a series circuit has components connected end-to-end in a single loop with no alternative paths. Key features include, first, one continuous path connecting all components sequentially. Second, no branches or junctions that would split the current. Third, current flows through each component in turn. The circuit diagram illustrates this concept. Notice the battery provides 6 volts. Lamp 1 and lamp 2 are connected in series, and the switch controls the entire circuit. The current path goes from positive terminal, through lamp 1, through lamp 2, through the switch, and back to negative terminal. Now we examine the experimental method for measuring current in series circuits. This follows Cambridge IGCSE standards. The apparatus needed includes battery to provide electrical energy, lamps as circuit components, ammeter to measure current, connecting wires for electrical connections, and switch for circuit control. The method consists of these steps. First, connect the ammeter in series with other components. Second, place ammeter at different positions to verify current readings. Third, record measurements at each position. Safety is paramount. The hazards include exceeding voltage ratings and creating short circuits. Therefore, you must check component ratings and ensure proper connections. The diagram shows the ammeter connected in series, allowing current to flow through it. Notice the red arrow indicating current path through all components, including the ammeter. Let's work through our first example. The problem states, an ammeter reads 0.5 amperes at position X in a series circuit. What current flows at position Y? We are given current at position X equals 0.5 amperes, and we have a series circuit. We need to find the current at position Y. Step 1. Apply the series circuit principle. In series circuits, current remains the same at every point. Step 2. Write the relationship. In a series circuit, current at X equals current at Y equals total current. Step 3. Apply the principle. Since current is the same everywhere in series, current at Y equals current at X. Step 4. State the answer. The current at position Y is 0.5 amperes, exactly the same as position X. Example 2 analyzes current measurements at multiple positions. The problem is, analyze current readings at 3 different positions in a series circuit. The data shows position A reads 0.3 amperes, position B reads 0.3 amperes, position C reads 0.3 amperes. Now we analyze systematically. First, identify the pattern. Looking at the data, we see all readings are identical at 0.3 amperes. Second, apply series circuit law. The law states current remains constant throughout a series circuit. Third, verify experimental results. Our measurements confirm the theoretical prediction perfectly. Fourth, conclude current behavior. This proves current is the same at every point in a series circuit. The graph shows constant current across all positions, demonstrating the fundamental series circuit principle visually. Mathematical skills are crucial in physics analysis. Let's examine 3 key skills for series circuits. First, current conservation. In series circuits, current 1 equals current 2 equals current 3 equals total current. This means current entering any component equals current leaving that component. The mathematical relationship shows current remains constant throughout. Second, ammeter reading analysis. When multiple ammeters are placed at different positions in a series circuit, they all read the same value. The position of the ammeter does not affect the reading because current is identical everywhere. Third, circuit troubleshooting. If one component fails in a series circuit, the entire circuit stops functioning. Current becomes 0 throughout the circuit because the single path is broken. This characteristic helps identify series circuit behavior in practical situations. Now practice what you've learned with these 3 questions. Question 1 is basic level. It asks, current at point P is 0.8 amperes. Find current at point Q in the same series circuit. This tests your understanding of current conservation in series circuits. Question 2 is intermediate level. It states, 3 ammeters in series circuit read A1 equals 0.4 amperes, A2 equals 0.4 amperes, A3 equals question mark. Find A3. This requires you to apply the series circuit principle to predict the third reading. Question 3 is advanced level. The question is, explain why an ammeter must be connected in series, not parallel. This tests your analytical understanding of measurement principles. For all questions, remember to show you're working clearly, include units in every step, and check your answers make physical sense. Physics principles power our modern world. Let's see how series circuits apply in practice. In Christmas lights, traditional strings use series connection where current flows through each bulb sequentially. If one bulb fails, the entire string stops working, demonstrating series circuit behavior. In torch circuits, the battery, switch, and bulb connect in series, creating a simple but effective lighting device. The same current flows through all components. In safety systems, emergency stops use series switches, where any switch can break the circuit completely, ensuring immediate shutdown. These applications show why understanding series circuits matters. Career-wise, this knowledge leads to electrical engineering designing power systems, electronics creating circuit boards, and renewable energy developing solar panel connections. The concepts you learn today become tomorrow's technological solutions. Let's review the solutions systematically. For question 1, the answer is current at Q equals 0.8 amperes, exactly the same as point P. This is correct because in a series circuit, current remains constant at every point. For question 2, we find A3 equals 0.4 amperes. Since A1 and A2 both read 0.4 amperes, A3 must also read 0.4 amperes because current is identical throughout a series circuit. For question 3, an ammeter must be connected in series because it needs to measure the actual current flowing through the circuit. Connecting it in parallel would create a short circuit and give incorrect readings. Now, exam success tips. First, always show you're working even for simple problems. Examiners award marks for correct method. Second, include units in every calculation step. Third, state the physical principles you're using, such as series circuit laws. Fourth, draw clear diagrams to support your explanations. Let's summarize today's lesson systematically. The key points to remember are, first, current conservation means the same current flows at every point in a series circuit. This fundamental principle explains why ammeters read identically regardless of position. Electric charge cannot accumulate or disappear, so current remains constant throughout. Second, Single path means series circuits have no branches, providing one continuous route for current flow. This characteristic distinguishes series from parallel circuits and explains why component failure stops the entire circuit. Third, measurement requires connecting the ammeter in series with other components. This allows the ammeter to measure actual current flow without creating alternative paths. For further study, review series circuit principles regularly, practice ammeter placement problems to build confidence, and prepare for the next lesson on voltage in series circuits, which builds on today's current concepts by exploring how voltage divides across series components.